Hello class, this is Miss Aya with today's video on section 9.2 geometric series. As you're watching the video, please remember to write down in your notes important vocabulary, formulas, equations, or theorems, and examples. Feel free to pause, rewind, or replay the video as often as you need so you can get a clear understanding of what is occurring. And at the conclusion of watching the video, write down a brief summary in your notes of what occurred in the video, and then submit that summary as well as a top question via the online whisk the day before class. All right, let's begin. The question we'll ask in class, what's the difference between a sequence, which we talked about last time, and a series? And basically, a series is the result of adding the terms of a sequence. Okay, so basically a sequence, you know what a sequence is, but a series is a sequence of sums. That's the best way I can explain it. So here's a very simple sequence. The sequence of the numbers 1, a sub n is equal to 1. But if I were to sum up in terms, then I would have a sequence as well, which looks like these values, 1, 2, 3, 4, 5, 6, 7, 8. And some of you may say, well, that's the sequence, a sub n is equal to n. But I got each term by adding up the n terms, the first n terms of the sequence. So 1 is by adding 1, and 2 is 1 plus 1, and 3 1 plus 1 plus 1. So the way that you represent that is a series, which is a sequence of sums, is by doing the addition signs in between and then doing the dot, dot, dot to indicate that there is an infinite series or an infinite sequence of sums. Let's use an example that you might be familiar with if you ever go to the hospital and the doctor prescribes some type of antibiotic. If you have an infection or anything like that, they will tell you to take the antibiotic several times a day until the antibiotic runs out. And the idea is the antibiotic will help eliminate the infection. So here we have, for example, 250 milligram ampicillin doses 4 times a day that the doctor tells you to do, which is 6 hours a day. And at the end of 6 hours, approximately 4% of the dosage remains in the system. So the question is, how much of the antibiotic is still in the system after the 10th dosage? Well, we can answer this using a series. Let Q sub n represent the amount in milligrams of the drug in the system immediately after the nth dosage. Okay? And let's take a look at what that looks like. Immediately after the first dosage, we have 250 milligrams. Immediately after the second dosage, we add another 250 milligrams for the new tablet, but then what remains of the first tablet is already in the system, and we add those two up and we get a total of 260 milligrams. So after the third dosage, our value is going to look like, again, we have a third dosage, which is 250 milligrams. And then what's remaining of the past 2 dosages, which is going to be this value. Well, another way I can represent that is if you recall that what's remaining of the second dosage of the first 2 dosages looks like something of this form, as we saw here. And then we apply another 0.04% because that's what's left over. And then we add this. So it seems to be very systematic what's going on, because it looks like we're having a multiplier to each term that we can simplify and we get a new value. And this is what's going on here. Here's that 250, and then here's the result of the first term, first dosage, second dosage. Okay, so we can keep on doing this, but it would be lovely if we had some type of formula to do that. And we do have a formula, and that formula can be represented using this type of format. We raise, again, this is the new dosage, and then this was the first dosage, how much of it still remains after 9 tablets. This remains after 8 sessions, 7 sessions, vice versa. So let's see if we can come up with a general term for this sequence, which is actually a sum of sequence values. So let's say I multiply the 10th term by that multiplier 0.04 or 4%. And then let's say I subtract So when I do that, then the exponent in each of the terms, or 0.04, increases by 1, okay? And let's say I subtract these two values. I actually take this and subtract it from this value. Well, then what happens is we have some cancellations going on, because we have some this minus this minus this minus this, vice versa, this minus this minus this, and we end up with just 250 here minus 250 times 0.04. So this is that same 250 and then this, okay? And then if I'm trying to factor out q sub 10, I get this, and then I get q sub 10 by itself, and I get something that looks like this. And I can compute these values for different values of n. In this case, n was 10. Oops, let me do a different color. 10, and then we have 10, 40, 40. This is really only the difference thing, and so we have some type of formula that looks like this, where n is only applied in that sense. So let's evaluate the 10th term, and we just use the formula and we get this expression. And I want to point out that this number is actually this rounded to the 1000th place. And let's see what happens when I change it from the 10th term, oops, to the 40th term. And all I have to do is copy and paste and then change the 10 to a 40. And I get roughly the same number, which lets us know that it seems to balance out around 260.417, around that much. So they're pretty much very close values. I'm sure if my calculator could be more specific, I would have more significant digits. But anyway, it's around 260.417. And if I wanted to check using my lovely generate sequence form, I do a list and spreadsheets, menu, data, generate sequence. I type in my sequence, oops, and press OK. And as you can see, the values start off at 250. Oh, what did I do? That's incorrect. I must have typed in something wrong. 260, oh, 250. All right, yes. And I get exactly the same values that we got initially. And then as you see, they all seem to kind of, if you look at the bottom value right down here, you can see that it's of different things, but then it seems to settle out around the 10th term with that value. Okay, so that's an example of a geometric series. And we have a way of computing the nth term without having to physically add up each of the n terms to get that value. Now the question is, what happens as n goes to infinity in this problem? We pretty much are confident it's going to be 260 point something. To figure it out, if we take a look at this, we can say, well, the only n term that's affecting it is this term right here. So what happens when this n goes to infinity? Well, because this value here, 0.04, is less than 1, between 0 and 1, then that means that as I raise this to the infinity power, this value is going to go to 0. So for n closer to infinity, this value is going to look like this, which is 260.42. Okay, so let's just generalize this. We talked about a geometric series here. Well, this is a geometric series, and the reason why is because it's being multiplied. Each term in the sequence is being multiplied by the same number, which ended up being our common ratio, which was x. And we do have a beginning term, and a represents the initial term. And we call this finite because we only had it up to, for example, 10 values, 40 values, 40 sums, whatever you want to call it. An infinite geometric series has no ending 10 or 40, so we indicate that by a ... So make sure if the difference between if you're considering a finite geometric series or infinite geometric series, it's the ... Okay. And we can use the same rationale to figure out the nth term is using this same thing where we take our initial value, multiply it by 1 minus the common ratio, and our drug problem was 0.04, raise to the n power, and then divide by 1 minus the common ratio again. And all this works as long as the common ratio, which was in our case was 0.04, is not equal to 1. If it's equal to 1, then we can't do anything with this. And then we can easily come up with this term for the sum, and we have this phrase. Now, what happens as n goes to infinity? Well, it depends on what the common ratio is. If the common ratio, the absolute value of that is less than 1, then you're going to have that x to the n goes to 0, and therefore as n goes to infinity, and you're going to end up with this value as our converging sum to be the case. If absolute value of x is greater than 1, then that means the series goes to infinity. Series values go to infinity, and that does not converge, i.e. it diverges. And if x is equal to 1, then it oscillates between a positive and a negative value, or these two values. All right, and we're almost finished. Let's take a look at an example. How do I figure out the nth term? And how do I figure out whether or not it will converge or diverge? Well, the first thing you need to do is you need to figure out what your a is and what your common ratio is. Okay, so those are the two things you need to figure out. Well, a is easy. It's the first term. So a is 6. And to figure out the common ratio, we just divide any two terms. We divide the newest term by the oldest term, and you will get the common ratio. Now in this case, when I divide -2 by 6, I get -1/3. 2/3 divided by -2, I get -1/3. So I have this information. It's infinite because the ... my a is 6 and my x is equal to -1/3. And so using this general formula, I can represent my sequence, infinite geometric series by either of these, the nth term by either of these expressions. They all represent the same. And to figure out if it converges, well, we know it converges because our common ratio is the absolute value is less than 1. And then to figure out what it converges to, we just substitute into this formula, a divided by 1 minus that common ratio. And that's where we get our answer. Okay, and that's it.